All right, so today we're going to talk about second order passive noise shaping and then passive noise shaping using switch capacitors. So this is section 6.2. Does anybody have any questions before we get going? Okay, so one of the benefits of second order, well, before I even go that way, a second order noise shape basically looks like the following. Um, I'm having a monk moment. So this is second order passive noise shaping. And so basically what happens is we have our output. So this would be the output of the modulator. We'll just say it V out of Z. And that's equal to V in of Z times Z to the minus 1 plus 1 minus Z to the minus 1 times the quantization noise spectrum. And of course, what do we call this term right here? What? Oh, the whole term. Modulation noise, right? Because that's the quantization noise. After we differentiate it, we get modulation noise. And a first order differentiation is first order noise shaping. For a second order modulator, we square this and we get second order. And what this does is if you look at the shape of the quantization noise, I'm only going to do it out to the Nyquist frequency, you end up with a first order noise shaping that looks like this. And then with second order noise shaping, which means you have the second differentiation, you get a curve that looks like this. The point is that the noise is less here, but remember it grows out here, so there's more stability issues because you still have the signals being fed back. So if you amplify the higher frequencies and feed it back, you have more stability concerns than what you have with the first order noise shaping. But if somebody asks what's second order noise shaping, it simply means the modulation noise is the quantization noise with a second order differentiation. Okay, easy. So let's talk about now a passive modulator. And so obviously, if we're going to do a second order differentiation, we're going to need, if it's an analog circuit, we're going to need to have at least two capacitors, right? So we can have at least two poles in our transfer function, or two zeros too. Two zeros rather, for differentiating the noise. Okay, so let's sketch the shape of a second order noise shaping modulator. There'll be two feedback loops, and one of the benefits of the second order modulator is it randomizes the noise a little bit. So we'll go put a capacitor like this and then a second one over to here, and then we'll take and we'll compare excuse me. We'll compare those two nodes, we'll call V1 and V2, to each other and try to drive them to the same value. Now here's our output, V out. This is our minus and our plus, and we're going to have two feedback paths. Now I want negative feedback, overall negative feedback, but I have to feed back, or I need to feed back to two separate nodes. So I'll feed back one output over here, and I want you to think about, why did I feed this output here and then over here? Yeah, it's getting kind of messy, but I'll draw it like that. I'm going to feed the output over here. So this would be, one, if I look at this, this is actually positive feedback, correct? Does everybody see that? Because I'm feeding back a signal. So if this signal goes too high, this output goes high, which pushes a current in here and does exactly the opposite of what I want. But why can I get away with that when I feed back the signal like that? Yep, exactly. So you see here, the signal I feed back, if I go forward, it's filtered by this transfer function here, and then this one isn't. It goes directly back to the summer, okay? And so let's analyze this topology and talk about it. Okay, are there any questions? And so one big benefit here is that, you know, all the tone stuff we had before, that's not as big of an issue with this topology, because now we have the two feedback loops that tend to randomize things a little bit more. Yes. No, you can tolerate the positive feedback as long as it's doesn't dominate. The negative feedback dominates, because the negative feedback here goes directly into the comparator, whereas this one has to be filtered, and so it's a lot weaker influence. Okay, so you know what? Why don't we, before I do any derivations, why don't we show figure 618? And you know what? Before I do that, let's revisit the first order modulator characteristics, which, let's see, where was it? 616. Just to refresh your memory. 616. Nope, I don't want that. I want something that sims fast. Okay, so this is just a simple filter, and we did this last time just to show what the linearity looks like. And then now what we're going to do is so notice first order passive noise shaping modulator. Actually, why don't I just go grab a new component? We'll use the same exact sim and go down to second 1-bit second order passive noise shaping modulator. Okay. Oops, why didn't that line up? Oh, because I didn't put it in there right. And then we don't need the common mode voltage because our comparator, just to prove that that's the same circuit we were looking at. There you go. So now take a mental picture of this. We'll hit run. And you can see by adding the the resistor and the capacitor, you just looking at that, you can see it's better linearity, right? So you'd want to use the second order for the performance rather than the first order, right? So you see the benefit. So what I want to do now, unless there are questions, is to derive the transfer function and look at the noise and the noise shaping. Okay. Yeah. So if you go look, let's go do that. See if so I look here. Oops. In here. And then you can see that they're switching, but both are staying around the average of the signal, whereas in the other case, one input is held constant, and so you can have the signal fed back and compared to the constant, and that gave us those tones problem we talked about last time. All right, so we'll go over this more later. So let's go derive that real quick. And the whole idea here is that if you are clever, you can get really low power analog to digital interfaces that don't pull quiescent current, essentially any quiescent current. So let's go ahead and derive let me sketch the signal one more time. Whenever I have to sketch things like this, I keep thinking to myself, man, PowerPoint's nice. And some professors actually think students love PowerPoint. They're proud of it. They say, I use PowerPoint, and they're like, it's great. And I'm like, okay. They're serious. I don't know, I guess some students like it. Somebody does. It'd be nice because it'd be a lot easier to teach. You could just read off your slides, and that'd be great. Oh, they thought I'm recording videos? That's a good idea. That's a good idea. Well, on low noise, I had to pre-record the videos, though, because I was traveling a lot more than I am. Well, more than I am now. I don't know a lot more, but all right. it's funny how everybody, oh, well, he's doing this bad and he's doing that. Okay. All right, so let's go ahead and write the all the currents that go into like node V1. Okay, so here's Vn, and I can write V1 is equal to the total currents that go into that node, which is Vn, so this is V1, V2, minus V1 over R, and then going in here is plus V out minus V1 over R, plus or minus, but we'll put it as plus V2 minus V1 over R times, so that's the total current times the current that leaves through here, which is 1 over j omega c. Does anybody have any questions about that? So I've got a question. What's the current that flows in this capacitor? It's all this, right? That current times 1 over j omega c is the voltage V1. That was a trivial question, just to make sure everybody's not falling asleep. And then I can write for V2 similarly. The current that flows, what is the current that flows in this capacitor? V1 minus V2 all over R plus V out minus V2 over R times one over j omega c. Looking good? Okay, any questions? So what are we going to solve for now? Okay, let me ask before we go any further, how would I write V out? V1 minus V2, oh, whoops, yeah, V1 minus V2, I'll start you out, plus how did we represent the quantizer? Yeah, plus the quantization noise that we add, right? So VQE of F. Anybody not understand this? So this voltage minus this voltage plus the quantization noise. Yay or nay? I hopefully put that in there somewhere. Yes, I did. The quantization noise added to V1 and V2 is VQE1 and VQE2. I used two different values for that, VQE1 and VQE2, and called it VQE. And then I want to skip, I don't want to do all the algebra, but is anybody not clear on this step? Okay, let me ask this. Would it be possible to use this topology for a multi-bit implementation? Like, remember last time we had the 4-bit ADC and 4-bit DAC. Would it be possible to replace the comparator with a 4-bit ADC or 4-bit DAC? Well, wait, think about how do we do that? Yeah, so you need two inputs. So what could I do if I wanted to try that, though? So everybody understands the ADC only has one input, and here I have two inputs. What could I try to make something work? Well, I could put like a diff amp or something, right? I can't do summing because I need the difference. So I could use a diff amp here, which would increase my forward gain, which is good. And then I would need the output of the diff amp would go into the ADC. And I'd amplify the difference. But then you ask, okay, well, if you're going to do that, why not just use an active op-amp topology, and you would get even better performance. Okay, so just thinking out loud there. All right, so let's go look. This, trying to come up with something that's useful here was a little bit challenging. So when you read this, you're going to find out that, here, I'll just actually show you in the book that, oops. this is what we get here. You get your output noise and your output signal. And as before, the output signal is low pass filtered. Is that a big problem? Nope. And of course, is there any difference? It's still first order low pass filtering, so there's no difference between this and the first order topology. Here the output noise is low pass filtered, but I see the spectral density is, well, wait a sec. This is still first order, so let me refresh my memory here. Oh, that's right. So on this, and there's a comment on the next page, you don't get true second order noise shaping, or there's a comment somewhere in here. Deadbands are better, but you're not going to get, yeah, this is it right here. You're not getting, it's the same as the first order. You just get better randomization. How can I tell it's the same as the first order? Yeah, it's the same 30 log of 30 log, same thing here, right? But you get better randomization, okay? Well, no, the thing here is you got to, you can use a 1-bit quantizer, but you can't use K of 2 or 4. Well, there's other problems with this derivation too. That's what I was saying. It's something to get you where you're going, but let me try to understand what you're saying. So there's assumptions made when you're deriving this, but I hope I was clear when I was deriving it. Well, if this happens, you know, on the bottom. Yeah. Wait. That's not true for 1-bit ADCs. But where did we? No. Oh, you mean for the VQE? Oh, that's just the assumption that's made. So, and the point is it just shapes the noise, so the magnitude of the noise will change. Yeah. Well, yeah, you could argue, well, there's other issues, but the problem is this topology isn't super practical. So you have to use, I don't know what you mean about the VQE, because VLSB would be VDD, but, oh, you mean here for the V noise RMS? But I think for the V noise RMF, we integrated that earlier. Here, VQER, we just borrowed this same kind of thing here where we integrated it and tried to find it. And going through here. So when you do that and you try to do the noise shaping, you get a different equation than if you assume a block wall bandwidth. It's all just, here's what happens if this is going to, you know, you could pick apart anything. So, all right. Okay, so if you look at it, you know, you get the benefit of better randomization, okay? Angshuman actually made he wrote a paper on this. Let's look at that, Angshuman, and you can answer questions. The stress. Where was that? Yeah, there we go. Boom. So he went through and did the derivation. So here's the basic conventional one with the response, and then he added the filtering here with the single feedback loop. So instead of having the 2 feedback loops, he still kept the 2 capacitors to further filter. And you can, I don't know if you can see well, but I'll try to show you. If you look, you can see the first order is the blue, and you see our little dead zone there. And then you see the second order is the green, and then the VN is a ramp, which is the red. And you can see the, well, hopefully you can see, let me zoom in a little bit more. You can see pretty good overlap there. So this would be the topology you'd use instead of the basic first order. All right. So let me, while we're here, let's just show you a few other things. So he laid it out, and then he had a comparator. This was the modulator here. Here's the total layout, and then he filtered it with a lot of filtering and was able to get pretty good differential nonlinearity, treating it, the output as a DC. We didn't really, probably could tighten this up a little, but it was already so small to begin with that we didn't do any more. And then you can see you got microwatt power dissipation for the conversion. So, do you have any other comments? Angshuan? No comments? All right, so you can see that's practical, very low power topology. It doesn't burn any current unless the comparator is switching or you got an input that's different than VCM, I guess. All right. Any questions on the passive second order noise shaping modulator? Okay, so let's talk about now using switch capacitors, because I just alluded to, or I guess I didn't allude to it, I said it, is that when you have a analog modulator, if this was at 0.5 volts and this was at 1 volt, the capacitor would start charging, and so you're burning power, right? So the next idea is, well, how can we reduce the power further and not have any static power dissipation? And the answer is to replace these resistors with switch capacitors. And just as a sanity check, for a switch capacitor, which looks like this, V1 non-overlapping clocks, what is the effective, so this is a resistance, what is the effective resistance there? Yeah, 1 over FC, right? Okay, so what is the time between, like if I look at V1, what is the time between the edges? Well, what is it? Yeah, 1 over F. Yeah, easy. I'm asking the trivial questions just to make sure that nobody's like, oh, he's asking. I'm not. No. Okay, so I'm going to replace these capacitors with switch capacitors, and then look at the topology. And so just to be complete, here it is. The comparator. And we had another capacitor here. And then a switch here for our feedback resistor. So this is a resistor going to our integrating capacitor. There's our clock. This goes to Vref. Then this is, what is this right here? Yeah, it's the feedback resistor, right? And V out. And so in your mind, this is a resistor. This is a resistor. And this is our integrator. So the idea here is since you replace the resistors, if you look at it and you're sitting there static-wise, you're not dissipating any power, right? Because there's no place for current to flow. So you have your clock frequency running back and forth. Well, if the switches, one switch is on, one switch is off, after you transfer the charge, you're not dissipating any current. So the idea there is, okay, I can design a modulator that could be used for remote sensing applications powered by ambient light or something, because it takes so little power. So I wanted to go through this topology. I want to modify it a little bit, and I want you all to help me derive the transfer function. So I want to look at the following. And we have a switch here, V2. And then we have a capacitor here. And then this goes to the inverting. Okay, so, well, let's figure out what's going to happen here. VCM, V out, and then this is C integrator, and this one is CI. And so I want to derive the transfer function for this. So tell me how to proceed. Okay, well, do I need to draw the timing diagram like this? On the last one? Well, you can derive it either way, I think. I don't know which way I derived it in there. All right, so, well, let's put the VCM in, right? Well, let me ask you this. Do you think it's possible for this water in the, the water in the bucket here to wiggle? In other words, do you think it's possible for this node to move around in this topology? I don't want you to think of math. I want you to tell me what's going on. Okay, wait a sec. So this is at VCM. Then when I close this switch and close this switch, won't I feed a pulse back around and have a capacitive divider? So won't I still get wiggle right here? Yay or nay? Here, let me put some numbers in. Let's say VCM is half a volt. Okay, so this is sitting at half a volt. And let's say this VN, let's just put it at half a volt as well. Okay, so there's no charge on the capacitor. And then let's say this is at, pick one, 0 or 1. 0. Okay, so if I close this switch, now these two open, this stays at 1/2, this stays at 1/2. Now I close these two switches. Now this voltage goes to, the other way, goes to 0. Won't that cause this voltage here that was at 1/2 to drop, depending on what the capacitors are, to drop down as well? Because the current flows like this. Does everybody follow that? And so, you follow that, Wenlan? Because the output of the comparator is 0. Yeah? So this is at 1/2. This is at 1/2. These two open. Then I close these switches because they're non-overlapping. So there's no charge on the capacitor. But now I'm taking this plate and I'm pulling it to ground. So I've got this situation right here. This is at ground. This is V minus, which is this node right here. This was at 1/2, and now I'm pulling it to 0. Ooh, sorry. So this was this capacitor C int. It's going to ground. This is V minus. This is CI. And then my output, this node, top part, this node here and this node here are both at 1/2. Then I close these two switches, and now I pull this plate to ground. When I pull this plate to ground, I'm going to pull a charge up here, and this is going to go down correspondingly. And it's going to go down by 1/2 times CI over CI plus C int. Remember, it's the opposite of a resistive divider. Does anybody disbelieve that? Because I got a simulation I can pull up and show you. We'll pull it up and look later. Okay, Wenlan? You don't believe it? All right. Let me pull up the capacitor here. Well, do you want to see the sim, or do you want me to do it again? Would you agree that this is V minus? This is going to the minus input of the comparator, and that's C int. Do you agree with that? This is all right? Okay, so when the switch is closed, here I've got CI. So that's this. And then this node here was at 1/2 when the switch was closed. Now it's being pulled when this switch closes to ground. So I go back and I look. And I say, oh, it's going from 1/2 to 0. Whatever this voltage was, I don't know what it was to begin with, is going to see a divider. So I can derive this in several ways. Why don't I call this as delta V in, and I'll call the change here as delta V minus. And the charge on this capacitor is delta V in minus delta V minus, minus, times Ci. That charge has to flow through this capacitor, which is delta V minus minus 0 times C int. Do you agree these have to be equal? Okay. So then I go, all right, I'm going to move the C int over, and I get Ci times delta V in equals C int plus Ci times delta V minus. Or delta V minus is equal to delta V in times Ci over C int plus Ci. And remember, it's the way I remember it is I know the voltage divider. This is equal to V in times R2 over R1 plus R2. For capacitive, it's just the opposite. It would be R1 over, or R1 divided by R1 plus R2. So this element's in the numerator with the resistor, and this element's in the numerator with the capacitor. Why is that freaking out like that? Yay or nay? All right, believe me? We'll find out. I'll show you in the simulation. Okay, so then I want to derive the, you guys help me out on this, all right? Tell me what to write first. Ci times, okay, I don't want to make a mistake, so what should I write here? What's that? Okay, but before I write that, I need a time part. So I'm going to write it as n minus 1 times t plus v common mode. Yay. And then at that time, I'm going to call this node here V minus. Does anything change on that V minus at that time? Well, let's assume that it's constant, and then we'll discuss that because it's not constant, we just said, okay? Okay, so now when, what's that? Well, it is, but there's the output changing, which will feed back around. We'll just not worry about that right now, because no, the previous, oh yeah, I'm getting ahead of myself, yeah. Yep. So we don't need to worry about that. Okay, so then when this opens, I get the following. I get Ci plus C int times V minus of what? Yeah. Minus V out of, well wait, I'm clocking it on Phi1. Yeah. And since you want to carry through the VCMs, we'll do that. And then before I go any further, I'm going to get out my red marker here and get rid of all the VCMs. And so I get Ci times, or minus Ci times, I'm going to go directly into the Z domain. Now these are equal. Times v minus of z, z to the minus 1/2, minus v out of z, z to the minus 1. Yeah, thank you. I need to blow my nose again. Okay. And so if I write then v out of z, that's equal to v in of z times z to the minus 1 divided by z to the minus 1, so those cancel, times oops, I got the capacitors in here. Oh, something's wrong. Yeah, I'll carry it through and look at it in a moment. And then that's plus v minus z to the minus 1/2 all times c I plus c int. Something's wrong. All over ci. Why am I pausing? Well, I moved this over, so it's v in ci z to the minus 1. Then I moved this over, so it'd be v out z to the minus 1 times ci plus c int plus. Oh yeah, thank you. We can just get rid of that. That was not what I was thinking, but oh wait, and I don't have this here either. So I made a mistake somewhere. How do I know that? Just no deep thought. No, look at this and okay, there's v out of z. How do I know that I've done it wrong? Well, there's no noise shaping, right? I don't see any integration or differentiation, rather, of the noise. So I'm missing a 1 minus z to the minus 1. So let me pause for a moment and look and see if I can figure out what I did wrong. So I got ci. Hold on, let me check something real quick here. This thing, I should have another v in there somewhere. So I don't see any noise shaping. I just see, oh, my input goes directly to the output, and my oh, that's not, shoot. We're not done there yet. All right. What am I missing, or what did I do wrong? Where's the quantization noise? Let's ask that first, right? I didn't add the quantization noise in. Yeah, so I got to put the v in plus quantization noise in there. Let me see, how am I going to do that, though? It's v int plus vqe. So this is just of the topology without the comparator. You know what? I don't want to spend any more time on this because it's not that important. So let's look at the results. We need to move on to the couple of things, but I want to simulate this first. So 621, I want to look at that. 622. So let me just pull those off the web. So I want, I don't know which one I want. Okay, this one is the basic, so it doesn't have a filter, so it has the RC, so you can run it. Oh, that's a sine wave. Let's see if we have a ramp. Yeah, 622. So this is the switch capacitor. So basically what I just derived is this, and I didn't put the quantization noise or phi. Show that around. I don't want to spend the time doing that. So let's hit run, and then you can say, gee, it works. Let's also, for the heck of it, plot the current that's pulled. Where is that? Spice, where's save device current, save default, save device current? Why am I not? You should be able to. Oh, there we go. Okay, so if you look in here, the key point is, you see in switching you get some current, but the rest of the times there's no current flowing. So I'm convinced there's a lot of simple, not high speed, but simple converters that can be done using these topologies. But I think there needs to be some creativity in looking for, how to connect things up and get real low powers. Because if you look, if you get a good comparator design here, you can drastically reduce the power, because even though it's a tiny little chunk of current, if you had, I don't know if I actually believe that, but if you had the ability to reduce this impulse here, even though it's tens of picoseconds in width, you would reduce your power even more. Let's actually, for the heck of it, just look. Press Control and left click, and it says the average is 269. That can't be right. Does that sound right? Well, I don't think you want to look at that. Yeah, but I don't. What's that? Uh, I don't know, because if you look here, I'm not convinced that it's RMS, because if you look at the current that flows, there's no way that. So okay, so does anybody know what's the simple way of thinking of RMS currents or voltages? What's the definition? So you take a DC voltage or current and you put it on a resistor, and you calculate the power, and you get a power, right? VDC squared over R. All right. For RMS, the way you calculate power, the way it's supposed to, is you take the RMS voltage, square it, and divide by the resistor, and it gives you the exact same power as an equivalent DC source. So the DC and the RMS are dissipating the same exact power. So when I look at this and I say the RMS is 1.1, I don't believe it. I think there's some problem there. Because you look at how much current's pulled, it's not pulled a lot on the average. And these pulses are tens of picoseconds in a microsecond scale, so I don't believe that measurement. All right, anyway. All right, so let's we got time, so let's cover one more topic. Are there any questions about this? This is basically just trying to flex your brains and thinking of other ways of doing things. One thing that draws power that's not seen here is what? Oh, the what? Oh, this filter. Oh, actually, that's a good point. I think, yeah, you're right. So if we just went and resimulated and put 500 MEG or 500 gig, we wouldn't see the output, but when you run, maybe the power's drastically, yeah, see, the power's tiny now. Right, because I filtered it, but you can still see the signal there, right? So the point is, I think there's something to be done here in low power A to D converters, but what's the big thing I'm not showing in here that draws power? You should know, Angshaman. I'll give you a hint. Phi1 and Phi2. Yeah, you need a non-overlapping clock generator. You can get, your NAND gates and inverters, but they'll draw probably as much power as all of this. So when you do the simulation, you have to generate your clocks as well. And then also the, I try not to bring my phone with me when I come to class. I don't know if you keep hearing it, but my phone keeps going crazy. Of course, have you ever had a professor that stops in the middle and answers their phone? That is ridiculously, and that's incredibly disrespectful to the students. Anyway, uh, uh, yeah, so you would have to reduce the power of the clock generator. All right, many times that bothers me, man. All right, any questions on any of this? So I want to talk just briefly about K-paths, and that's related to your course projects. And so I'm going to basically, I'm going to go through, and I want to do this as simulator based because I want to talk about this again. What did I put in the schedule? Yeah, so I want to basically just talk about some simulation stuff, and then on Friday, if you can make it, that would be good. I want to talk about using K-paths and improving linearity, but I want to do this from a qualitative point of view to discuss things. And before I do that, I want to give you an example of the basic idea of why this is useful. Now, again, on the projects, I'm not going to give you something I know that I know the path this is going to work. I'm going to give you something that's actually a graduate research project that could lead to significant, contribution. So I don't know if it's going to work. That's the funny thing. Funny thing about research, and people don't know, is that part of research is failing. It's like when you design in engineering, you design experiments, and all your experiments for testing something are successful. You didn't design your experiments right. You got to design the experiments so you see failures, right? So it's not all about success. All right. Failure is what you want. Failure is an option. All right, so I want to go through this simple op-amp circuit here just to refresh your memory. A, and then plus, minus, R1, R2, V out. That's why I don't fear failing. All right, so if I ask what's this voltage right here? Okay, if I call this voltage V fed back and this voltage V in, then in terms of A, what is V out? Does everybody agree with that? Okay, and then in a real ideal case, A is infinite, but in a real op-amp, A is not infinite, so I want to derive this. This term right here, I'm going to call beta, which is equal to R1 over R1 plus R2. So I'll write V fed back as V out times beta. Everybody cool with that? So then I can write V out is equal to A times V in minus V out times beta, or V out is 1 plus A beta. That's equal to A V in, or V out over V in is equal to A over 1 plus beta A. You've all seen this. Yeah, maybe we should meet tonight because I don't think I'm coming in tomorrow. I need to get over it. So I'm going to rewrite this as 1 over A plus beta. So if A is big, then this approximates to 1 over beta, or R1 plus R2 over R1 plus R2 over R1, or 1 plus R2 over R1, the standard gain. Okay, everybody sees this, right? So if A was 10,000 versus 9,000 versus 100,000, it doesn't really matter. You're still getting a gain set by this. So this is real simple, but it's supposed to be, this will be related to why the topologies we're selecting works. The key point is, in the forward path, the gain isn't critical, but in the feedback path it is. Because the beta ratio, this ratio, the feedback path is important. Does everybody get that? Okay, so one of the problems with doing using the noise shaping topologies is speed, right? Your input signal is going to be slow, got to be slow compared to your sampling frequency. So we're going to attempt to get around that problem by messing with the feedback. So let's go look at the chapter 6 here. And I want to first talk about 623. Let's go here. Whoops. Okay, so if you look here, here's the idea. What I'm going to do is I'm going to take a single input path, 1 sigma right here. Now I'm going to feed it to the forward. So the forward path is basically all of this. And then once I get to here, it's all digital, right? So the forward path goes from here to the output. I'm going to take advantage of the fact that the forward path can make mistakes and be sloppy. Does everybody get that? My A doesn't have to be precise. My feedback paths are the ones that are critical. So what I'm going to do then is I'm going to take my feedbacks here and I'm going to feed back a signal that on alternate phases of the clock. So if I look at my signal and my overall, so this is 4 paths, and my overall clock, my main clock looks like this. With 4 paths, I'm going to be clocking right there in one path. Then I'm going to generate another clock which is right in the middle in a path there, then another one that's there, and another one that's there, and another one that's there. So if this period was T, because I'm clocking on 4 phases, my effective period between the phases is T over 4. And so that gives me 4F sub S. Okay, so if I was generating the clocks with inverter delays and I had a 10 picosecond inverter delay, I could effectively get 100 gigahertz sampling frequency. So the benefit there is now if I'm at 100 gigahertz, I can really do some wider band conversions. Does everybody follow that? Okay, so if I go back now and I look at this, okay, this again is a passive modulator. Let's go through and see how it works. But this comparator makes a decision, is it above or below? Notice these 4 paths are 40K. They come back around on different phases, and the average signal that comes in is divided, the average here, the outputs, divided by the 40Ks in parallel. So if I look, here's my red is the summation of the digital signals, and now you can see right up front, well, wait a sec, I don't have just a 1s and 0s, so my quantization noise has got to be less. The green is the filtered output, or the filtered red. So let me just see if I taught well. If I look at this, is just adding all the 4 bits up and then outputting a value, and this just does the digital to analog conversion so I can look at it easier. In terms of digital signal processing, how do I think of this? What do I think of this as right here? So I'm adding up the first bit, the second bit, third bit, the fourth bit, fifth, or the first, second, third, and fourth, and I'm changing them. Is this really a filter? Okay, so let me, if I look at the digital output, let's see if I plotted that. Let's look at just the digital output alone. My clock frequency is changing at 100 megahertz. So if I look at the width of one of these lines here, for my output, so that's not a good one. Right here's a good one. So the period of my main clock is 10 nanoseconds and I have 4 paths. So the distance between rising edges is 2.5 nanoseconds. If I look at this distance is 2.5 nanoseconds, so my effective sampling frequency is 400 megahertz. Okay, so my output's changing at 400 megahertz. Let me ask a simpler question. Is this a filter of 1 minus z to the minus 4 over 1 minus z to the minus 1, an averaging filter of 4? Why or why not? Okay, so I've got the bits coming out here, and I'm adding, let's say, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, bit 8, bit 9. I'm constantly adding the bits up. Tell me what you think of this as. So let's say they're all zeros. So the first bit comes out, it's added up. Then the second bit comes out and adds up. And the third bit comes out and adds up. So let me sketch it another way. What's that? What's that? Yeah, it's an averaging filter because I'm summing all 4 bits, right? But let me prove it to you. So does everybody see I'm adding all 4 bits together at any given time? Does everybody see these bits, because the clock phases are staggered by 4, are going to change every 2.5 nanoseconds. So the rate at which the sum, this is just a cheap D to A converter, the rate at which the voltage out changes is going to be 400 megahertz every 2.5 nanoseconds if there's a change on the input. So if I go back now and I look at it, my first one comes out, my second one comes out, I add it, my third one comes out, I add it, my fourth one comes out, then I go back to the beginning in the fifth. So the first output after the startup is that. The second output is this. Then my second one changes. My third output is the sum of that. So tell me, what kind of filter is that? Yeah, it's an averager, right? It's just averaging the 4 inputs. Okay, but the big difference is, so I get my 4 here, it's averaging. This is at, it's not at, it's going to be at the, whatever the corresponding, it's going to be at f sub s, I think, is the right one, because it's 4 times higher. So it's not a frequency of 4, it'd be 4, if I'm doing, check this, I'll put a question mark there. Instead of f sub s over 4 for an averaging of 4, it's 4 f sub s over 4 because of the equivalent higher speed feedback. Does everybody follow that? Okay, so is there decimation here? There's no decimation. The key point I'm trying to get across, and again, I'm going to cover this next time, but the key point I'm trying to get across is when you're doing these high-speed things and you're looking at the bits and you see somebody adding bits together like this, you don't just go, oh, okay. You know that they're filtering your data. Okay, so it's going to come through and you're going to get an attenuation if you put a higher frequency sinusoid in here that's going to roll off at the sync filter just by adding things together, okay? So just as a sanity check for myself, what is this right here doing, these 4 resistors? Well, it's a digital to analog converter, right? This voltage, this current plus this one. So the LSB is weighted less than the MSB, so I get more current through the 10K. This is just a simple A to D converter, or D to A converter rather. Okay, so this is a DAC just so I can display the data. Now normally, and what you'll probably do in the projects is I've got MATLAB scripts, you'll read the data out and you'll use MATLAB to process it from LT Spice. So it interfaces to LT Spice, you read it out, and then you can massage the data from there. All right, so let me comment on some problems. 4 paths is nice, but 8 paths would be better. The problem is, once you start putting more and more paths, the delay around the feedback loop, and in a practical circuit, this thing responding limits the efficiency, or limits the effectiveness of the topology, okay? This is equivalent to me being like cloning myself 3 times and have 4 people there looking at the bucket where they do it right in sequence. You know, one is at 0, 2.5 seconds, 5 seconds, 7.5, 10. I could do it at every 10-second interval by myself, but if I have 4 people working, I can do it 4 times faster. So I'm getting an effective time interleave topology by focusing on the feedback path. Now, if I make a mistake, the mistake isn't on one path, it's shared between all of the paths. So that sharing will allow me to compensate for the mistake in the other paths. Does everybody follow? So if the second of me in the clone looks in the bucket and says, oh, the water level's too high, and it really isn't, then the following decisions will average that out. Does that make sense? Okay, so first thing, notice that if I make a mistake in the forward path, it's not a showstopper. And that my feedback paths need to be as precise as possible. Now, one thing that you'll do in your projects is, and we'll talk more about this later again, is instead of, you see how this signal goes high and it stays high? Well, how long does Vout1, I just want to make sure everybody follows, how out would Vout1 stay high or low? Let's double click to give you an answer. Wait, how long would Vout1 knowing the clock, it's clocked with phi1. It stays the whole 10 nanoseconds. It doesn't change until the following rising edge of that 10 nanosecond clock. Now this one, same thing, except it's delayed by 2.5, but they all only change every 10 nanoseconds. That's the point. You want those forward paths to operate slow. You want them combined and feeding back to have a very high sampling frequency. So this path of this comparator doesn't have to operate at 400 megahertz. Does everybody follow that? So if I go back and I look, that's not very interesting. Oh, because I'm zoomed out. If I go back and I look at the width here, this width is 10 nanoseconds. If I go look at the next one, let's go look at this one. And I look, it's 10 nanoseconds too, but it's shifted by 2.5 nano. Okay, so here's the issue. When you are designing your projects, which I'm working on, if you have 8 paths, say, which is a reasonable number for a lot of applications, when you have such a long delay between each path making a decision and the information being fed back, you end up feeding back garbage because you're continuously, if you think of it as a bucket, you made a decision 10 nanoseconds ago, whereas 8 nanoseconds later, you don't know if that's still relevant. So what you want to do instead, and this is what's done in continuous time delta sigma, is you want to feed back a chunk of charge and then stop feeding anything back. So what you want is you want to take and you want to say, I'm going to feed back this much signal, and then it's going to last for 2.5 nanoseconds. So I make a decision and then reset. Okay. Then after the 2.5 nanoseconds, you're going to go look at the next path. Does everybody follow that? Because you can do 2.5 nanoseconds in the logic because it's just set reset. It's digital. You can have it reset on the next clock edge, or if you want a wider pulse, it could be 2 clock pulses down. Okay, so the key point is, if I think, okay, I'm going with this topology, this guy makes a decision, and then he says, okay, I go high. Well, it feeds back that high for the entire 10 nanosecond clock pulse. Well, by the time it comes back around, it's still putting in that old information. It's not really that useful. So what we want is we basically want, instead of this to be continuous, we want it to have a cup or a bucket, and we want it to make a decision and dump it and be done. So that the only thing that has, each of the forward paths are slow, but the feedback paths send a precise amount of charge, they dump it in, you're done. Does everybody follow that? Any questions? Okay, so let's look at a couple more and then we'll quit. I just want to plant this in your head. Okay, the forward path doesn't have to be precise. We can make mistakes. I get the high-speed sampling by putting it in the feedback path. Using multiple paths allows me to increase my sampling frequency. I'm not going to get real high resolutions, but if I'm doing something like I got a digital bit stream in here and I'm trying to detect it, I might be able to get, with 4 bits or 6 bits A to D converter and get it all digital. And once it's digital, then life is good because then I can use DSP to extract, where are the edges? Okay, so that's a good question. I say that. How do you detect the edges in the digital data? What's that? No, I mean, assuming you got the edges coming in, your data's coming out, how would you detect the edges in the data? Now remember, in a real SerDes, it's not full logic levels. The SerDes is a serial deserializer, so you get a bit stream coming in, and if it's through a channel like your HDMI that you plug into your TV, that you connect to your computer, the amplitudes of the digital stream will depend on how far away the TV is from your computer or your video place. So the amplitudes change. So you're changing the amp, you're digitizing it, but you want to determine ones and zeros. How would you do that? I'm asking a trivial question. How do I determine? What's that? Yeah, differentiate. Put it in a differentiator. Then I get my edge, right? It comes down, then I get my next edge. Oh, well, then I know where the edges are. I can set up my timing information. There's other things that you can do with it once it's digital. You can do, I need more gain. Well, you can gain it up. I can adjust digital. I can adjust the amplitudes of the signals that I'm feeding back to the input. Okay, so life is good. All right. So let me see what other topologies I have here. So, okay, so this one is the exact same thing as we saw before, except I've got this register here that I clock with phi1. So I'm adding up all the bits, and then I store the bits in this register that's triggered on the rising edge of phi1. So what's the difference between this one and the previous one? No, you're still storing all the samples, so it's exactly the same. You sample 1, sample 2, sample 3, sample 4, clock in. Sample 1, sample 2, sample 3, sample 4, clock in. So in other words, instead of doing this, you do, I'm going to sum this 4, then I'm going to sum the next 4, then I'm going to sum the next 4, because I'm taking that and clocking it in the register, so the output then that goes into the DAC will change at 100 megahertz. What's the difference? Is the filter changed? Is the filter changed? I'm still adding these together. Yeah, well, the filter's still this, right? But what is putting that register in do when you clock the 4 data and then you clock the 4 data? Yeah, it's decimating. Your input rate's coming in every 2.5 nanoseconds, and your output's coming out at 10 nanoseconds because you're clocking it. So the point here is all this stuff we learned, it's not useless. You're going to use it, all right? Very practical. So here you see I'm adding them up. That's a filter. I know what that filter is. But here I add, to retime the data, I add this register. So I go look now and I run the sim. And I look, and now my pulse widths, I'll zoom in here for a second, that's my digitized, are all going to be 10 nanoseconds. Okay, so I go from, let's zoom in even more, 40 to 50 nanoseconds. They're all changing. So now I'm essentially I'm decimating, and so I'm slowing things down. I'm filtering it even more, which is maybe useful, but it kind of defeats a little bit of the purpose of the multi-paths. Okay, any questions about that? Does that make sense? Yay? No? Holy crap, I gotta go home and read the book. Alright, I think that's it, but let me check and see. Oh, this is inactive. We'll cover that next time on Friday as well. Okay, so I wanted to plant that. Try to read the book, because if you do, one of the things you'll see that is an issue is if the comparator has too high of offset, then it repeatedly makes the same decision over and over again. So we're going to ultimately go to a, this is just showing if you put a gain in the forward path, it reduces the effects of the offset. We're going to eventually go to some sort of active integrator to try to minimize the wiggling here to keep our SNR high. Okay, and again, I'm going to go through and see what I can do with the transistors, but doing all this stuff is very time consuming, so bear with me. I'll get it to you as soon as possible. So any questions? All right, have a good day. Hopefully we'll see you on Friday in TB 178.